Good morning, good afternoon, good evening, wherever, whenever you get to see this. I wish you well and welcome you to the last part of graph sketching. Today we are making a summary of everything that we've covered so far. It's been a long chapter. It actually lasted somehow like 3 weeks or something. So we have learned a lot, and today we're going to bring it all together. So, I would like to present you today with the steps to actually sketch the graph of a function in the form of the following summary. So, steps to follow when sketching the graph of a function. To follow when sketching the graph of a function. There are a few steps that we need to be concerned with. The first one, find the domain of f. Find the domain of the function. Now, remember that when we reviewed this long time ago, it seems, back in August or something, the domain of f of x, we want to be concerned with really just two things. The first one, if you have a root, a square root, you don't want the inside of the root to be negative. So just make sure that the inside of the root is always positive. This is a concern for the domain. So make sure the inside of the root is positive. And if you have something on top that is divided by something at the bottom, then the something in the bottom should actually not be 0 because we cannot divide by 0 in mathematics. So when we talk about domain, we basically talk about those two things, right? There's plenty of other things we should be concerned with, but in the confine of this course, just make sure that the inside of a square root is always positive, and that if you have a ratio of polynomials, that the bottom is not 0. That's basically what we need to keep in mind for the domain. Okay, so you have your domain. Now, I'm going to say find, if possible, because it's not always possible, find, if possible, the x-intercept of the function and the y-intercept of the function. Just want to point out something you already know. X-intercept, you need to make y is equal to 0. And the y-intercept, you need to make x is equal to 0. You know that. Just a little reminder as we go along. So, at this point in time, you've identified the domain of the function. You have been hopefully able to find the x and the y-intercept. Let us see if we can find all asymptotes. Find all asymptotes. Now, again, little reminder, we have two types of asymptotes. Yes, we have a vertical asymptote, which happens when? Who remembers? Ask yourself, do I remember how do I get a vertical asymptote? And if you said, well, you have found a number, x equals a, such that the limit as x approaches a of the function does not exist. And you're also going to try to find if there are any horizontal asymptote. When does that happen? When you have a horizontal line, y is equal to b, such that the limit as x approaches either plus or minus infinity gives you that precise value B. So two types of asymptotes. We don't do oblique asymptotes, although you may have seen that in high school if you took AP calculus. We're not covering that in our calculus, so just vertical and horizontal. Once you have that, then you actually hit the core of the problem. You hit the calculus core, so you find f prime and f prime prime along with their critical numbers. Along with their critical numbers. I remind you that a critical number for f prime or f prime prime is a number that makes the numerator 0 or the denominator 0. We've seen that extensively. I'm not going to write it down. 5. And second to last. Write the table of variation. Write the, I'm going to call it the sign. That's an S. That's an S. Come on, make an S. That's the sign table. So table of variation. That is actually very, very, very useful, as you've seen in the last example in the previous video. Specifically, the last line of the table of variation tells us so much about the shape of the graph. And finally, when you have all this, put in the graph all key points. What do I mean by all key points? Well, all key points are local min that you have found in the table, local max, and point of inflections that you also have identified from the table of variation. And sketch the graph. Et voila. And sketch the graph of f of x. If you follow all these steps, you can't go wrong. You will actually end up absolutely getting the correct graph for the function that I'm going to ask you to graph, basically. So, 6 steps. Domain, intercepts, asymptotes, derivative, both of them critical numbers, table of value, table of variation, and finally, the graph. We do all this, we are in business. All right, let's see if we can apply this on an example. Let us get rid of that. Okay. All right. Very good. Alors, example. For those keeping track, those problems, they're pretty much all 3.5. Not because they're that difficult, really, but as you can see, as you will see, as you're about to see, as it will be shown to you to see, it's pretty long. Each problem will take us like 12 to 15 minutes easily. Sketch the graph. Sketch the graph of f of x is equal to x squared over x squared minus 1, showing all relevant features. All right, so this is a lazy way showing all relevant features. This is a kind of a lazy way to say show everything. Show the asymptotes, show the critical numbers, show the derivative, the min, the max, the pi, everything, the whole 9 yards, the whole shebang, and then sketch the graph. Okay, so showing all relevant features. Okay, well, here we go. Step 1. first thing we want to do here is take a look at the domain of this function. Remember that the domain, we are concerned with the inside of a root being only positive and the bottom of a polynomial to be non-zero. I don't have any roots, but I do have a denominator. So here, the domain actually tells me that the denominator cannot be 0. Okay? So what does that mean? It means that x squared minus 1 cannot be 0. That means that x minus 1, x plus 1 cannot be 0. And that means that x cannot be 1 and x cannot be negative 1. So the domain is a bunch of x's that I can put into the function. We all know that. And what we have found here are the two exceptions of these x's that I can put into the function. If I put 1 or minus 1, I'll be dividing by 0, which is a no-no. Alors, what is the domain? The domain is all the real numbers except them two values we have found that must be excluded. So that all real numbers except minus 1 and 1. That will have its importance, basically, when the time to sketch the graph comes. All right, step 2. Let's take a quick look at the intercepts. We have two types. So what about the x-intercept? I need to make y is equal to 0. So 0 is equal to x squared over x squared minus 1. Crisscross, cross multiply, and you will get what? 0 times this is gone. X squared times 1 is x squared. So x squared is equal to 0. So x is equal to plus or minus the root of 0, which of course is 0. We have an x-intercept and it is located at 0. Good. So if the x-intercept is 0, let's take a look at the y-intercept. It should be pretty clear what we're going to get. This time I need to replace x by 0, so 0 squared over 0 squared minus 1. This is 0 over minus 1. So basically we have that the origin is the intercept. So x is equal to 0 and y is equal to 0 are the intercepts for this graph. Good? Not too painful so far? Step 3. Well, now we're hitting some calculus. Step 3, we need to take a look at the asymptotes. So, asymptotes. Let us begin with the vertical asymptote. Actually, let me do it over here if I want to be able to do them both on the same whiteboard, which is so small. Vertical asymptote. How do I find a vertical asymptote? Well, I got to find the limit as x approaches a, but I don't have the a, so first I must find the a. How do I find the a? I make the denominator equal to 0. And since we've done this right here previously, when we looked at the domain, we know that this happens at 1 and minus 1. So we're going to be intelligent, that we're not going to work for no reason. We are going to use the work we have done in step 1 to identify the two numbers that have a chance to become asymptotes. But without the justification, basically, my answer will not be validated. So I need to find the limit as x approaches. Let us test this first one, and then we'll test the second one. So x squared over x squared minus 1 in both cases. And this will be quick. Now we cheat, right? We cheat, we replace x by 1. That's going to be 1 over 0. That's going to be 1 over 0. Check mark, check mark. And now I have a reason why those two numbers were excluded from my domain. It's because they are vertical asymptotes. So I have two vertical asymptotes. Two vertical asymptotes. X is equal to 1, X is equal to minus 1. Let's take a look at horizontal asymptote. This time I don't need to make the denominator 0 because a horizontal asymptote is the outcome, if it exists, of this limit. I'm going to start with positive infinity and then I'll take a look at negative infinity. Okay, x squared over x squared minus 1, cheat, put it in, infinity over infinity. We are well aware of this. It is undetermined, and that means that I need to do more work because that is not an answer that I can accept. Okay, the more work is well known. It's always the same thing, divide top and bottom by x to the highest power. So what is the highest power in here? 2 in the top, 2 in the bottom. I shall divide everybody by x squared. So x squared over x squared, and then x squared minus 1, each one will go over x squared. I will end up with the limit as x approaches infinity of 1 over 1 minus 1 over x squared. I will cheat. I will get 1 over 1 minus 1 over infinity. What is 1 over infinity? That is 0, isn't it? So 1 over 1 minus 0, this. Okay, I should also be doing the limit as, not enough room. The limit as x goes to negative infinity. I should also be doing the limit as x goes to negative infinity of f of x, but I will not do it because it's a polynomial over a polynomial. The only time where those two have a different values, you remember from the previous video, it's when we have a square root. We don't have that here, so you can verify that if you do the negative infinity limit instead of the positive infinity, you'll get the same answer. So, conclusion, we have one horizontal asymptote at y is equal to 1. So this is a pretty fruitful step. It gives us a lot of information concerning this graph, which ends up having not 1, not 2, but 3 asymptotes. 2 vertical and 1 horizontal. That's going to be quite a graph with 3 asymptotes. All right. Good. Good. So let's get rid of this and move on to step 4, where we shall do some derivatives. Actually, I have what I believe you will find a pleasant surprise. Because, as we often do on exams, in order to save some time, we actually provide the students with the derivatives. Yeah? So step 4, the derivatives. We are supposed to find them, right? But on an exam, basically I'll have a whole number on the exam asking you, find a derivative of this, find a derivative of that. So there is really no point in a problem like this to ask you to find a derivative again, because I've already tested your knowledge of that before. And also the purpose here is not to know if you can do derivatives. The purpose is to see if you can interpret the derivative and extract from that the information you need to sketch the graph. So assume, and please don't, on an exam, if this is given, don't check it, don't calculate it. It's going to be correct, okay? Assume that f prime of x is going to be given as what I'm about to write down, and f prime of x is also going to be given as what I'm about to write down. So the prime is minus 2x over x squared minus 1 squared, and the double prime is 3x squared plus 1 with a 2 outside. X squared minus 1 cubed. That's given. So again, if on any exam, if they give you this, you do not have to check those. They will be correct. They will be validated. I will make sure that I calculate these 3 times so that there is no mistake. Now what we still have to do in this important step is what? Even if we are given the derivatives, now we have to find from each one the critical numbers. So critical numbers from f prime. Okay, this is of 2 types, as we all know by now. You must make the numerator 0, and you must make the denominator 0, so that the derivative itself is 0, or the derivative is d and e. Alors, what's the numerator of f prime? This is f prime. This is the numerator. Very easy equation to solve. Divide both sides by -2. And you have your first critical number. Denominator. F prime is here. The denominator, x squared minus 1 squared égale 0. That means that I will get rid of the square outside here by taking the square root on both sides. So plus or minus the square root of 0, which of course is just 0. Again, this is the 3rd time we are meeting this guy in this problem. We met it in asymptotes, we met it in domain, so we know that there are 2 answers. And then that gives me a ton and a half of critical numbers for f prime. Even if these numbers are not in the domain, even if they don't have the slightest chance to become a local min or a local max or anything of interest, they must be included in the table of variation, because around them the signs can change, and that will be crucial for the sketching of our graph. So the critical numbers are here for f prime. The critical numbers are here for f prime. What about the critical numbers? Critical numbers from f double prime. Again, it's the same story, it's the same music, just different lyrics. Numerator 0, denominator 0. And I now look at my numerator of f prime prime, which is here. So 3x squared plus 1 égale à 0. Divide both sides by 2. That's 3x squared plus 1 égale à 0. That's 3x squared is equal to minus 1. X squared is minus 1/3. Stop. Why? Because I cannot take the square root. I cannot take the square root plus or minus of a negative number. No critical number. I could have stopped right here when I saw that x squared is a negative. X squared is never a negative number. And as for the denominator, well, gee, how many times must we deal with this guy? This time to the power of 3. So x squared minus 1 is the cube root of 0, which is 0. Yada, yada, yada. X is equal to 1. X is equal to minus 1. These are the 2 critical numbers for f double prime. We don't have a critical number arising from the numerator because we got the root of a negative number, but we have 2 critical numbers arising from the denominator. So that's good. That's a good portrait of the derivative. We're going to consider step 4 finished, and we're going to put these critical numbers in the table and sketch the graph. I will need the prime and the prime because I will need the signs in the table of variation. So step 5, you know what, I'm going to change colors because my black marker is slowly dying. So step 5, table of value, table of variation. All right, so let's see what we can actually do here. Let's put it over here, maybe some space for step 6 if we can. Okay, what are my critical numbers? Critical numbers are -1, 0, 1, all the way down to here. So these are all the critical numbers, notwithstanding if they come from prime or double prime. Now, for the first prime, we had the 3 numbers that were actually critical. So that was a critical number for f prime, so was this, so was that. And for f double prime, and for f double prime, we also had -1 and 1, but we didn't have 0. So we're going to make one table, like we did before. And now what we're going to do is just put in some numbers in there. Jean, let's pick a number between -infinity and -1. Let's pick -2, and let us put that into f prime. We put a -2 here, ladies and gents. I'm going to save you the trouble of calculating this on the calculator. We are going to get a positive sign. If you put a minus here, you're going to get a plus as well. If you put a 1/2 here, you're going to get a minus. If you put a 2 here, you're going to get a minus. And what does that tell me for my function when the derivative is positive? Well, if you said increase and increase and decrease and decrease, you are correct. So right away, what can I tell? I can tell that the function goes up and then goes up, then it goes up, then it comes down. That guy is going to be a local max. And that go down and that go down, so nothing happens here. Good. Now for the second derivative, which is here. Putting -2 into this will give me a positive. Putting -1/2 into here will give me a negative. Actually, I could have put 0 because I got this entire interval from -1 to 1. So negative here. And after that, it's a positive again. All right, so what happens when the second derivative is positive? We are concave up. Then we are concave down. And we are concave up. Good. The table of variation is taking a good solid shape. I want to add, like I did before, one last line to this table of variation. I'm going to call it the line for the graph. And that's going to be crucial for step 6. So I bring down all the subdivisions that I had, not minding at all where they come from, the first prime or the second prime, I don't care. And then I do what I did before, which is, okay, I am concave up, I am increasing. Which half of this upwards parabola is increasing? This one. So that's going to be the shape of the graph between -infinity and -1. In here, narrow little corridor between -1 and 0. What am I? I am increasing, I am concave down. Which half of this is actually increasing? The first half. Here, I am decreasing, concave down. Second half. Here, I am decreasing, concave up. First half. You see what this is? This is step 6. This is the graph of the function right there. All we got to do is bring it all together. Now, before we do that, one little remark. Let's go into here. Step 6. Before we do that, one little remark. Notice that the concavity changes around -1. So one would be tempted to say that minus 1 is a point of inflection, right? Right? Wrong. Minus 1 is not a point of inflection because minus 1 is a vertical asymptote. So there is no y value there. So it looks like it should be a pi, but it isn't. And the same thing for 1. Hello. What's going to be the graph of this guy? Here's a y-axis. Here's an x-axis. Okay. We are going to put a couple of points that we know. Why do we know that 0, 0 is actually a point on the graph? Because it's the x-intercept and the y-intercept. We also know that x is equal to minus 1 is a vertical asymptote. We know that x is equal to 1 is yet again another vertical asymptote. And finally, that y is equal to 1, longer bars, just to differentiate the vertical from the horizontal. So let me just get rid of this and put it a little higher so I have a little more breathing room for my graph. This is still current step 6. Okay. Hello. So this is actually the setup, right? I also have a local max, which corresponds to both the x and the y intercept. So this is something I'm going to have to account for. But basically, like I said before, the graph is already done. How so? Well, between negative infinity and minus 1, I got to sketch this graph. And clearly, I got to respect my asymptotes. So where do I put this so that I respect my asymptote? Do I put it here? Well, then that means it would have to cross my horizontal asymptote. That's possible. But if it's possible to avoid that, then I will. That segment of the graph should be here because then it respects the vertical and it respects the horizontal. You can see here that the limit as x goes to minus infinity is going to be that line 1. Now this, between minus 1 and 0, respect your asymptote. So you do that between minus 1 and 0, respecting the vertical asymptote, connecting with the local max. Other half of the parabola here, going down, respect the asymptote by leading towards it. Finally, this guy, between 1 and infinity, respect your asymptotes. Can I put that over here? Can I do this? I guess I could, but I would not respect my horizontal asymptote if I did that. So I'm not going to do this. I am going to respect my asymptote by putting it right there. You can see the symmetry, right, between this and that is like on its own. And that, mesdames et messieurs, is the graph of f of x. Okay, so solid problem that brings together, I would say, limits, derivatives, just about everything we've covered in Calculus 1. So we'll see more of these examples in class, and in the meantime, well, try to perhaps look at this video a second time to absorb it better, and I will see you soon. You have yourself a good day.